This can... Hello, welcome back to spectroscopy. I'm, of course, David Irvin, your lecturer that will be guiding you through this process. The first thing I'd like to do is kind of go over what is due this week. We actually just have a lecture this week. We will have our first homework set, though, due at the end of the week next week. So other than just coming to class and looking at the videos from the class, there is no other due date for this particular week. However, I will be assigning homework problems, and you'll get that assignment on Tuesday of next week. Or if I get really invigorated over the weekend, I might send you an email out over the weekend. Okay, so any questions that we have before we begin? No? Okay. So I'm going to go ahead and share my screen. I sent these slides, I put these slides up on Canvas. These slides are up on Canvas. There's week one, number 1, week 1, number 2, and I'll be doing this ahead of time so you will have an opportunity to download the slides ahead of time. Notice that they're on this nice Texas State background. I'm converting all my old slides to the new background, which is why they're not already all posted. So I'll hopefully get those finished up quickly and have all 9 chapters converted over and up on tracks so that you can start reading ahead. Again, the lecture notes, the actual slides, just give the condensed version of what's in the book. And so there's a lot of stuff in the book. But what I want to do is every time I finish the section, I want to stop and actually show you how to apply it using the tables in your book, using unknowns that you haven't seen before, using so you don't have to memorize everything, you just have to know where to find it in the book and how to utilize it. That's the most important thing about this. Okay, so let me go ahead and share my screen. I'm going to share my iPad via cable, and let's see if it likes it today. Come on. All right, yay. My iPad's happy today, so it gave me that. All right. So I'm going to put our gallery view up over here. So if you have a question, of course, go ahead and either raise your hand in the participants or put something in the group chat. I should be monitoring that. And if I am just rambling on way too long, go ahead and unmute and ask your question if you can. So, all right. So last lecture was mostly about all the different instruments and detectors and different ways that we would have these to be able to look at mass spec. Today, what we're going to look at is structure determination with specifically electron impact as the ionization technique, because it has a lot of fragmentation in it that other methods don't have. And so we're going to look at that fragmentation as a method to determining the difference between molecules. And then what that's also going to lead into is that, we're also going to do an exercise at the end of this where we're looking at just, okay, given a mass spec, where do we start? Okay, we don't have an empirical formula, so let's generate an empirical formula. Let's figure out what the hydrogen deficiency is. And then let's start piecing the different fragments together and looking at the different fragmentation rules and how they apply to different structures and how we can differentiate them by looking at our fragmentation table in our book, as well as remembering our 9 fragmentation rules. Okay, so that being said, let's go ahead and continue on. The first thing I want to talk about is the hydrogen, the index of hydrogen deficiency, or the hydrogen deficiency index. I'll use both. And basically what this is a calculation to help you figure out whether you have rings or double bonds. It's basically if you had a fully saturated hydrocarbon, so a straight chain, C10 straight chain, you're going to have, the 2 hydrogens on every single carbon along that chain plus the 2 at the end. And so you're going to end up with, something like 22 hydrogens for those 10 carbons. And so that would be a saturated system. However, most of the systems we look at are not saturated. There's at least 1 double bond, a carbonyl, or a ring. And each of these things will take away from that fully saturated hydrocarbon to give us a hydrogen deficiency. Okay. So when we do this, we have a formula for this. And the formula is, oh, where am I going to go? Oh, there it is. Right here. And this is something that you kind of gotta know right here. And what we're gonna do is I'm gonna show you how to apply it. But it's the hydrogen deficiency is equal to the number of carbons in your empirical formula, half of the hydrogens in your empirical formula, minus half of the halogens in your empirical formula. Now, the reason we're subtracting those is because they only bond once, and they are they are the ones that will take up a single site in a carbon that it bonds to. Now we have plus 1/2 nitrogen. Now nitrogen, of course, wants to bond 3 times, so we're adding 1/2 of nitrogen plus the number 1. Okay, so what this means is by taking our empirical formula, plugging in the number of carbons, the number of hydrogens, number of halogens, number of nitrogens, plus that number 1, we should be able to see how many possible rings or pi bonds we have. Okay, so for example, if we did this with benzene, benzene has 6 carbons and 6 hydrogens, we would end up with a hydrogen deficiency of 4. And I'll calculate that out in a minute here. And what that means is that we have 1 hydrogen deficiency for just forming the ring, and then 1 hydrogen deficiency for each of the pi bonds. And so that's what we're looking for when we're looking at hydrogen deficiency. Do we have rings? Do we have double bonds? Do we have a combination of the two? Okay, so if we do our calculation and we have a hydrogen deficiency that is 3 or less, that means we don't have a benzene ring. Okay, if we do have a hydrogen deficiency of 4 or greater, then we want to start looking for fragments that are associated with benzenes or benzenes with CH2s next to it. So a benzene would give us a nice fragment of 77 right here. A benzene with a CH2 adjacent to it, so a benzylic carbon, will give us a 91, and we'll talk about that today. And then we also have another fragment of 105 that we can look for. But before we get too far along that, let's go ahead and actually do a calculation with these hydrogen deficiencies to see where we are. Okay, so now notice that in this calculation there is nothing for oxygen. Okay, the reason oxygen is not included in this calculation is oxygen always bonds twice anyway. And so it's basically a net 0 as far as double bonds go, and therefore we don't have to include that in our calculation. So only hydrogens, halogens, and nitrogen and carbon are included in our calculation. Okay, so this one's already done here for this compound here, but we can do it for a couple other ones. Let's go ahead and do something a little different, like C6H4N2O2 bromine right here. So if we did our calculation for this, it's going to be a little bit different because we have a halogen in there, we have oxygens in there, but of course we ignore the oxygen. So what I'm going to do is I'm going to blow this up, and I got to write down what we're going to do here. C6H4N2 C6H4N2OBr. Let me see if that right. O2Br. Oh, O2Br. Okay, so our hydrogen deficiency index calculation is going to be equal to 6 because of the 6 on the carbon, and we're going to minus 1/2 of the 4 hydrogens we have, minus 1/2 of the halogens we have, plus 1/2 of the nitrogens we have, which is 2, plus 1. Okay, so I don't think this is going to work out. This is going to give us a half number, but let's see if we have it. So this, of course, becomes 6. Half of 2 is 2, minus half of 1 bromine is 1/2, plus 1/2 of 2 is 1 plus 1, which gives us minus 2.5 plus that. So it's 8 minus 2 and 1/2, which gives us 6 and 1/2 right here. Now, When we end up with a half in our hydrogen deficiency, that means we have a charge on our system somewhere. We have an ion. We don't have a full molecule. But in this case, we ended up with a total of 6 as our hydrogen deficiency, which means we have the possibility of having 6 double bonds somewhere in the system. So we're probably looking at something like a carbon with a nitrile on it, because that would be a carbon and a nitrogen, and that will give us 2 deficiencies. So C triple bond N. We could have a ring in the system. We have 6 carbons, so there could be a ring in the system. We have 2 oxygens, which means we could also have carbonyls. Carbonyls would each count for one of those unsaturations. Okay, so that's why it's important to have the hydrogen deficiency, so you're starting to look for different functional groups within the system. So it's good to have one when it comes up with this half number, because that tends to make your molecule here probably an ion and not a fully saturated system. I see a hand up. I can't hear you, you're still muted.
Sorry, I just wanted to make sure, is it not 5.5?
Let's see, 8 plus 1 plus, it's 8 minus, that's 6, but there's 2 plus 1s here, aren't there? Because this plus 1 is for the nitrogen. This plus 1 is for the nitrogen. And this plus 1 is just the one at the end here. So the half is for the bromine and the 4 is here. So that should be 6 plus 1, which brings it to 8 minus, 6. Still not 5 either. Oh, because this was a 6. Okay. 6 minus 2 is equal to 4. Plus 1 equals 6. So it's minus 1/2. So it'd be 5.5. You are correct. Yes. Yeah. So, yeah, algebra is going to kill me on this one, but we'll see. All right. So thank you. No, that is correct. It's 5. I left out one of the additions. Okay. So that's why this example here, I actually put them all with the colors for the different ones, so that make sure we got each and every one that we have. Okay. So again, when we have a hydrogen deficiency, we're starting to look for rings or pi bonds. And if we have a hydrogen deficiency of 4 or above, we start looking for things like benzene, because benzene is a fairly common molecule in a lot of organic chemistry. Okay, so that's telling us, once we get our empirical formula, how we get to what we're going to, okay? So the next thing is, how do we get to our empirical formula to begin with, okay? And just if we have a mass spec and it only gives us our molecular ion peak, we can try to back calculate out some plausible molecular formulas for that system just by doing what we call the rule of 13. Okay. So the rule of 13 is we would take the weight of the ion and divide it by 13. So let's say our ion weighed, in this case here, we have an ion weighing 92. So if we take 92 and divide that by 13, we're going to end up with 7. And that's going to give us, let's see, 91, which gives us a remainder of 1. Okay. So that means that that's going to give us a fragment that has 7 carbons and 7 hydrogens. That's what this 7 up here means. And then we have to add the remainder. Oops, that's, this should be a 7. So the 7 that we're having in our division up here gives us the first number. And then by adding the remainders to this number here, we get a plausible first fragment for that molecular weight. Okay, so by adding the 1 here, our plausible molecular weight, or the starting formula for this, would be C7H8. Okay, so that's the first rule in trying to get to our molecular formula. However, very rarely do we have things with just carbon and hydrogen, and this has a pretty decent hydrogen deficiency index for this particular fragment. So what we want to do is look for other atoms that might be in there instead of just carbons and hydrogens. And so we have a substitution rule for this, okay? Okay, and the substitution rule is the idea that, okay, I know there's nitrogen in this compound because I put nitrogen in this compound. So what you do is you start replacing these different fragments of carbon and hydrogen with the same molecular weight of the heteroatom that you are going to add to it. For example, if we're going to add an oxygen, the weight equivalent of an oxygen is 1 carbon and 4 hydrogen. Oxygen is 16, carbon is 12, and each hydrogen is 1. So that means that they are weight equivalents. So if we take away 1 carbon and 4 hydrogens, you can add 1 oxygen to your empirical formula, and you haven't changed that ion's mass. Okay, so that we have substitutions for different types of compounds. For example, nitrogen has a molecular weight of 14, so we're going to do 1 carbon and 2 hydrogens. If we know we have oxygen and nitrogen, let's say we have a nitro group in there, we know we can substitute for the equivalent to that would be 2 carbons and 6 hydrogens. Fluorine has a molecular weight of 19, so 12 plus 7 hydrogens makes 19. And then it gets also silicon, phosphorus, sulfur and oxygen. Now, once we get up to halogens right here, fluorine and iodine only have 1 isotope, okay? So when fluorine and iodine have 1 isotope, we have to replace these using the carbon replacement rule from the rule of 13. However, when we have chlorine and bromine, we have different isotopes, so we can actually see the isotope split, and so we don't have to use that hydrogen replacement directly because we can see them available to us, and we can add them to our empirical formula to start with, okay? So do you see where we get this first chance at an empirical formula of any fragment we have just by taking it and doing that simple manipulation and substitution? Okay. We're going to do this as an exercise at the end of the class too. But I wanted to introduce the topic here and show how we do this substitution. Now, is it right the first time? Sometimes. And then what you do is you look for fragmentation patterns that support your premise or other things as we add like IR. Does it have an alcohol in the IR? Well, yes, though we need to do at least 1 replacement with an oxygen. So you're using this to help build consistency with each of the different pieces of data you have. You're adding them all together to build a consistent spectroscopic argument to why you think it's that particular compound. Okay, so this is one way to start giving us what our empirical formula is. Another rule that helps us with this empirical formula is what we call the nitrogen rule. Now this works in compounds that have carbon, hydrogen, oxygen, nitrogen, sulfur, halogens, and phosphorus, okay? Now, once you get up to some other elements, this rule doesn't really apply, okay? But what is interestingly true, like about 20% of the time, is that if you have 1 nitrogen in your compound or an odd number of nitrogen in your compound, you're actually going to end up with an odd numbered peak. So for example, if you had 1 nitrogen in a compound, you could have peaks that were 101, 131, 171, or 155. If you have an odd number, chances are you have 1, 3, 5, etc. number of nitrogens. However, if you have an even numbered fragment value, then you could have 0 nitrogens or an even number of nitrogens, 2, 4, 6, 8. So this is not particularly true for things that already have quaternary ammonium salts in them or radical cations. So if you know you have a radical in there, a radical cation or a quaternary ammonium salt, this rule would not apply. But it's a really nice general rule to say, oh, it's an odd number, I might have a nitrogen in there because, you know, for specifically a parent ion peak. Now, once you start breaking them apart, one of the fragments might turn out odd and one of them might turn out even. And that means that the odd fragment is the fragment that the nitrogen went away on. So that nitrogen fragment you can see because it'll continue to have some odd numbers in them. Okay, so that's the nitrogen rule. And it, again, only works about 80% of the time, but it's a good way to start, looking at this. Okay, so now we get to the next rules here. Now, these 9 rules of fragmentation are guidelines, okay? Are guidelines. Anyway, and so what we can see is you can, your first pass, when you first look at your mass spec, you'll say, oh, huh, that's got a very, intense molecular ion peak, right? And so we might say, oh, that might be a long linear chain. Okay. So if we have a good, the molecular ion peak is larger for straight chain hydrocarbons than branched hydrocarbons, okay? So, and the reason for this is number 3 here is that cleavage is favored to give you the more stable radical cation. So that means a tertiary radical cation is more stable, meaning that the more branched it is, the more likely it is to break at that fragment. That's why the linear ones tend to have a higher molecular ion peak than branch systems. Okay. Now, that intensity decreases with that increase in molecular weight. Okay. The reason the intensity decreases with the increasing molecular weight is it's harder and harder to get the entire ionized fragment all the way through the analyzer to get there. So as your molecular weights get smaller, you're more likely to see that molecular ion peak. As molecular weights get higher than, more than 200, that peak is going to decrease in activity, and you'll see it less and less. Sometimes you'll barely see that molecular ion peak at all in things above 400. Okay. So rule number 3 is cleavage is favored for branched, and that has everything to do with the idea that we're going to see the tertiary carbocations are more stable, and therefore it's easier to make that fragmentation. The other thing about that is that if you have a straight chain, you're more likely to see it clip, 14, 14, 14, 14, 14, because there's no favored part of the branch. If you have something that has a T-butyl group on it, you're going to see it split that T-butyl group off first. And you're going to see this huge loss in mass that would be associated with the T-butyl group because you can form that tertiary carbocation. Okay, so those are the first 3 rules of fragmentation, and we're going to play with these in our exercise later today. Okay. Now, the next rule is your aromatic rings, double bonds, and cyclic structures actually tend to have higher molecular ion peak, or much higher than, not necessarily higher than the base peak, but they are very well pronounced. And the reason for this is once you have a ring in it, it's actually harder to break this ring off into fragments, and so it actually is a little more stable. And aromatic rings in particular have resonance stability in addition to the ring stability. So a lot of the times you will see the molecular ion peak for the aromatic ring and some other double bond structures and conjugated double bond structures. Okay. So that's rule number 4. Rule number 5 is when you have a double bond, either on the end of a chain or in the middle of a chain, what you're going to see is instead of having just that double bond break off as 2 carbons and 3 hydrogens, you're more likely to see a 3-carbon fragment break off. And that 3-carbon fragment breaks off because of allylic cleavage. It cleaves 1 bond over from your double bond right here, so it'll cleave here, giving you rise to these radical cations that are stabilized because they have resonance. And so that makes it a much easier fragment C. And so you're going to see with double bonds, especially terminal double bonds, the breaking off of 3 carbons and 5 hydrogens as a major fragment in your system. Okay. And if it's in the middle of a chain, you might actually see it be 3 carbons and 4 hydrogens instead. Okay. So if we have a ring in a system, just like in one of the previous rules there, the rings are really, really stable because it's kind of hard to figure out where to break it without, it's nice stabilized to have this ring in closed. So what we'll see is that we'll actually break off any side chains, alkyl side chains, off a ring first. This happens also for aromatic rings, but it happens in a slightly different way, which is another one of our rules. Okay. The only thing that really doesn't follow in that is if your ring is unsaturated. If you have at least one double bond in that, it can undergo a retro-Diels-Alder and snap apart into a diene and a dienophile. And so it'll be the butadiene plus an ethylene will come out. And this is also really common, but it only happens if you have one or two double bonds in your ring. If you have three double bonds in your ring, that's a benzene, and that's much more stable. Okay, so it's an unsaturated ring with, but not benzene. Okay, which brings us to benzene. Okay, aromatic compounds, if it's just benzene by itself, you're going to see that benzene come off as a 77 fragment. It's going to be really, really common. However, if you have a CH2 adjacent to that benzene ring right here, what you're going to see is that's the benzylic carbon. That has special reactivity and special stability. So what we're going to see is it's actually going to break that at the between the alpha carbon and the beta carbon, between the benzylic carbon and the alkyl carbon, to give us this fragment right here, which then rearranges to form a tryptilium cation. Okay, this tryptilium cation is incredibly stable. You can actually isolate these things. And so whenever you have a system where you end up with a 77 peak for benzene and a 91 peak for benzene, you know it had a CH2 adjacent to that ring. And what you can see is actually on some things, you can tell if there is a CH2 there because it will have a 91. And let's say you had instead a carbonyl or a halogen, if you have that, you won't see the 91. So that really gives you a good handle on whether or not there's a CH2 adjacent to the benzene. Okay. So let's move on to rule number 8. Okay. So rule number 8 is a little hard to see at first, but what you'll see is the fragments you get out will have a certain stability. You'll see them breaking out as charged species. And so in the case of if you have a regular carbon-carbon single bond and it's adjacent to a heteroatom, specifically oxygen or nitrogen, what's going to happen is the lone pair from the oxygen and nitrogen is going to come in and help form a double bond and break off that other fragment as a radical. Okay, so what we'll end up with is our major charged species is going to be the one with the heteroatom in it. And then the other fragment leaves as a radical, which you typically don't see unless it has a positive charge somewhere else. So what we'll see is that you'll start looking for fragments with like 2 carbons and an oxygen or 4 carbons and an oxygen because the oxygen is going to carry away with the carbon system because of this heteroatom cleavage. This also is found in carbonyl compounds and ketones and aldehydes. We'll see that kind of fragmentation happen a lot. Okay. Oh, all right, which brings us to our 9th rule. Okay. 9th rule is seems a little simple when we probably should have started with one, but I think it's best to do it at the end because it's a little more complex than it looks. And the idea is that if you can cleave a small neutral molecule off, just like when we did regular organic chemistry, if you could have water leave or CO2 leave, these were very common ways of changing the molecular weight of a system or creating an alkene. So in Rule 9, if we can cleave off a small molecule, it will do it, okay? And the way it does it is by what we call the McLafferty rearrangement. Now, in the McLafferty rearrangement, the key phrase here is that you have to have a hydrogen that's a couple carbons over from where your carbonyl is. Now, the reason you want to do that is just like when we did in organic chemistry where we did the thermal decarbonylation of beta ketones, we did that because we could form this 6-membered ring and have the hydrogen actually transfer from the carbon to the oxygen on that system, allowing us to have ring cleavage. Okay, so let's look at that again right here. So the idea here is, it really doesn't matter what this group is. What you want is at least 3 carbon chain here. It can be longer, but you want to be able to form this 6-membered ring such that the hydrogen will come over here and it will fragment our material right here, giving us a fragment that has this group on it. And this can be an aldehyde, a ketone, or a carboxylic acid, or an amide. And then the shorter chain will come off as an unsaturated small hydrocarbon. Now, this right here is kind of, in this case, it's a resonance stabilized enol, and it'll also decompose after that. But again, it doesn't really matter what this Y is, as long as there is a hydrogen on this carbon here, you can get this fragment to come off and give you basically a methyl ketone or a methyl group here when it rearranges. Okay, so those are the 9 basic rules of fragmentation, and we're going to see them again and again and again. And you don't have to memorize them by name, you just have to recognize when you see them in the system. Okay, so I introduced halogen splitting last time, and I'm going to go into it in a little more detail now. And what we'll see here is, just like we used them in the rule of 13, fluorine will substitute for a carbon and 7 hydrogens. Iodine actually replaces like 10 carbons. Iodine has a molecular weight of 127. So that's going to be one of those major fragments you kind of look for, is that 127. Fluorine is kind of harder to see because it's got a fragment of 19. And so there's usually a lot of different fragments in that lower molecular weight section. But they only have one major isotope, so we don't see any kind of splitting at all. However, both chlorine and bromine have major isomers that we can look at. So chlorine in particular has the 35 and 37. So what we're looking for is one that's about 2/3, like this. That's indicating you have 1 chlorine here. And they are an M and an M plus 2 peak. So M stands for mass, and mass plus 2 gives you this pattern for chlorine. If you have 1 bromine, because this is 100 and about 95, we actually see almost even peaks at M and M plus 2 for bromine, okay? So that's if we have 1 of those. Now, if we have 2 of those, what happens is the patterns get a little more interesting, because now you have your M plus 2 is overlapping with your M, and then you have an M plus 4 peak show up here. And the same thing happens with bromine. So the patterns we'll start to recognize with the number of bromines are like this. So I'm going to blow up just the chlorine for just a minute here. So of course, for chlorine, we have our just single chlorine. It's going to be about 2/3, 1/3 at the M plus 2 peak. And so if we think about that, that when we get to adding a second chlorine, we're actually going to have about a 1/6 size peak of the major ion peak here. And then this peak grows in because it's the second, it's going to be 3/6 or 1/2. So that second peak grows up a little bit because of that second chlorine. Okay. By adding that third chlorine, we're adding more to this peak again. And so we end up with almost even peaks here. But we have, this is about 1/3, and this is rarely do we see it. It's typically supposed to be about a 6, but it's rarely that high. But we see it. And then by the time we add our 4th chlorine here, we have so much more mass at this M plus 2 that it becomes our major peak in that splitting. But we do see our M plus 6. No, this is our M plus 4. This is our M plus 6. And we occasionally, if our resolution is good enough, we'll see an M plus 8. And then the pattern gets a little more distinct as we get bigger and bigger. So, but the idea here is this, number one is found in the book, and you're looking for that 2, 2, 2, 2 addition, okay? Not an M plus 1 and M plus 1, it's an M plus 2, M plus 2, M plus 2. Okay, now when we look at bromine, the pattern is a little different because we're starting out with about, 198%, almost 50-50 here. So that when we add that next bromine here, the next bromine is going to give us a peak here, and then the other peak is, we're adding that peak. So we end up with this pattern here. So we get the M plus 2 peak becomes our big peak, instead of being equal to our M plus 2 peak in just one. Okay, so our M plus 2 peak is approximately equal in our first one, and then the M plus 2 peak grows in that system. And this is approximately the same. The M plus 4 peak is approximately the same as the M peak. Now, the pattern gets similarly very symmetrical when we add that third bromine here. Again, we grow both of the two M plus 2 and M plus 4 peaks, and we start to see the M plus 6 peak. Now, if we start mixing halogens, and that's what this demonstrates here, we see it adds to each other. So if we're looking at a bromine and a chlorine here, the bromine portion of this contributor is that section there, and the chlorine part of the contributor is the other half of it. So it still maintains the still type of pattern. It's just they're laid on top of the other halogen. And then for a bromine with 2, again, this portion and this portion were the same as the bromine system. Sorry about that. That one is the same as the bromine here, and then the others are added by the 2 chlorines. I said that wrong, didn't I? Yeah. I was right the first time. All right. So this part and this part is from the 1 bromine, and this part and this part is from the 2 chlorines. Okay. So that's the reason that these additive splitting patterns change with going from a single chlorine or a single bromine. You just start looking at trying to add those peaks together as they continue to add more and more. So you can, if you're starting to see a pattern where it's an M and M plus 2 and M plus 4, or then you're starting to look for peaks that are getting to the idea that we have either a chlorine or a bromine. All right, questions on halogen splitting? Okay, so we have our fragmentation patterns, which lead to certain fragments we're going to start to look for. We have our halogen splitting patterns we have, and we have our empirical formula that we generate from our rule of 13. Okay, so let's use those little things and look at this spectrum here and just see if we can't figure this out just from what we've learned so far. So the first thing we see here is we have a peak at 200 and a peak right around 170, okay? So if you wanna type something in the Zoom chat, first of all, I think we have a halogen in the system. Which halogen do we have? Heck. So just from the splitting, we don't have to know exact numbers here. We're looking at this. There's a little bit of there's a little peak in here and in here. So I think this is an M and an M plus 2, and this is an M and an M plus 2. So what halogen do we think we have just by looking at this mass spectrum? Bromine. Iodine. Okay. Now, if we were looking for iodine, we're looking for a 172, right? Or it's a 127. Iodine's 127, and I don't see a 127. Okay. But that M and M plus 2 being almost equal tells me I think we have a bromine in there. So let's look at that. So, and one of the things we're going to look at a lot is this Appendix B in our book here. Because our Appendix B is where we're going to look for our different fragments and look for different things that we have. Okay, and if we look at iodine, it should give us a 127 peak here. And I don't see a 127 on our system. So I'm going to go ahead with bromine. Okay. So let's see what we also have here. We don't really have a strong 77 peak, but it's there, right here. But we have this strong peak here, which tells me that's probably a 90 or a 91. So we have bromine on our system here, and then something falls off. And then we still have bromine on our system, and then bromine falls off, and then we don't have bromine on this part. Okay, see what I'm looking at? Because we had bromine on that high fragment, and we had bromine on that mid fragment, that means we lost something, but not bromine. Okay, so what is the difference between the 200 and the 170? That's approximately 30, right? So if we look at our fragmentation panel here at the Appendix B, a common fragment at 30 is, let's see, we got a CH2 with a nitrogen on it, a CH2, a C2H5, a CH. So let's look and see if we can break off something that looks like a methyl group or a propyl group there. Or an ethyl group, yeah. We have a loss of about 30, maybe that's 29 actually, which tells us we're breaking off a C2H5 fragment. And if we look at the structures down here below, let's see if we move it up there without doing anything. If we were breaking off a C2H5 from this one, the bromine would come off. So we wouldn't still have the bromine on our structure. Okay, so let's try to break something else off. If we were to break something off here, that would be breaking off a C3H7. And we don't see that loss because a C3H7 fragment, if we look in our book here, is an actual 43. And we don't see that as a major fragment. If we broke this off here, it would, this doesn't have a hydrogen on it, so we're not going to see that tropylium. But if we were to break this one off, we're going to be using that fragmentation rule of benzene having an alkyl chain, and it's going to give us our 91 plus the weight of our bromine here, and this is going to lose a C2H5, which is about 21. So I think what's going to happen is to get from here to here, we've lost this peak here. To get from here to here, we then lose the bromine, which giving us the tropylium, which gives us this strong peak at 91. Okay, so this is the kind of thought process we need to get into when we're trying to discern what we have structurally from what we see in the mass spec. We are looking for plausible fragments that come off that follow our rules of fragmentation. Okay? So, and we'll again do more of this in an exercise. Right here. So I want to do one more little demonstration of the McLafferty rearrangement, and it's because we want to look for certain fragments coming off. Okay? So the key here that we want to look at is if R is just a hydrogen right here, then the fragment we're breaking off is a C2H4 or C2H3 right here. And if we look in our fragmentation panel here, C2H3 is the loss of 27. Okay, so that's telling us we have a C2H3 fragment coming off. If that is not a long chain, it's a small chain. Okay. If it's slightly larger, we're going to add a carbon to the thing we're getting off. So that should be a C3H6. So where's our C3H6 fragment here? C3H5 fragment is number 41. So we're going to see that come off as a fragment. Because the methyl group's taking up one of these hydrogen slots. And so if it's longer than that, it'd be a C4H7. And so that fragment in our table here is, let's see, C4H9 is a 57 fragment. Okay. So you can see that in this case, the longer that chain gets, the different size fragments you're going to break off, because it's breaking off at the exact same place to be able to transfer the hydrogen over to our oxygen system. All right, now let's change gears and look at a different part of the thing. If we have a fragment where this group is a hydrogen or a halide, and this group is a hydrogen, we're actually going to have a fragment come off at 34, okay? So what does that mean, okay? Well, if we look at our table here for our fragment that's 34, common fragment that's 34, that's going to be, well, hydrogen sulfide. That can't be it. So that's going to give us something that's a carbon, oxygen with a carbon, so 2 carbons and an oxygen, right there. And if that group is a hydrogen and this Y group is an oxygen here, we're looking at a carboxylic acid. And so we're going to see is a decarbonylation product, which is that loss of 60, which if you look at it is the C2HO2H. So it's basically losing a fragment that's related to a carboxylic acid, okay? So that's how to look at the different fragments leaving from a McLafferty rearrangement as to showing you where the chains are. Are they on the carbonyl side or are they on the carboxylic acid side? Okay, questions over fragmentation rules, questions over halogens, or questions over fragments removed during McLafferty? No? Okay, good, good. All right, so what I'm going to do is I'm going to change gears now, and I'm going to pull up my practice, and we're going to work through this. So you can unmute if you want, or just kind of tack along as you want in here. So what I want to do is I want to go through, use everything we just talked about today in an example on this page such that we can look for, I'm going to need this with my fragmentation. So, all right, so let's pull up this first question here. It's like, okay, an organic compound is composed of carbon, hydrogen, and nitrogen, and carbon is approximately 60% of the mass. And the molecular ion peak shows a mass to charge ratio of 112. So the first thing we need to do is come up with a plausible molecular formula. So how are we going to come up with a plausible molecular formula? We have a rule for that, right? The rule of 13. So let's go ahead and try a rule of 13 on this first little fragment here. So we have 112 right there, and we're going to divide it by 13, okay? So let's see, that would be, let's see, 8. Let me get a calculator out. Yeah, that'd be 104, because it would be 24 plus 80, so that'd be 104. And we'd have 8 remaining, okay? So great, that's giving us a great place to start. All right, so remember, the 8 up here is going to give us C8H8 on our rule of 13, okay? But we have to add the remainder to the hydrogens here, okay? So that means our perfectly good starting place for this particular exercise is the idea that we're going to have C8H16, okay? Great place to start. Problem is, we have nitrogen in the system, and we only have about 60% of the material being carbon. So that means we can't have this as our empirical formula. We know there's another element in there, and we know we have too much carbon at this point. We have about 90% mass carbon. Okay, so now we have to do that substitution rule, okay? So because we don't have nitrogen, we have nitrogen is equal to 14 molecular weight, which means a CH2. So to add a nitrogen, we take away a carbon and take away 2 hydrogens to get to our first possible one. So that'd be C7H14N. Okay. So, and we think about this, well, carbon's still a little high. It's still like 80%. So it probably can't be this as our empirical formula. So we got to do that substitution one more time. So if we do another substitution, we have to take another CH2 out of there, which is a C6H12N2. Okay. So nitrogen's about 30% of the mass, carbon's about 60% of the mass, and hydrogen's about 10% of the mass. Okay. So just using the rule of 13 and substitution, we now have a plausible molecular formula for our molecular ion peak of 112. Does everybody see how we use that? Okay, this is key, because this is, you can just be, spinning your wheels a lot if you don't have at least some way to rationally go step by step. Okay. So now that we have this rational step by step, and we think that that's definitely a plausible one that meets the criteria we ask for in this thing about having 3 different elements and only 60% being carbon. So the next thing I ask is, how many rings or pi bonds must there be? What I'm really asking you to do is calculate the hydrogen deficiency index, right? So by knowing what our hydrogen deficiency index equation is, where hydrogen deficiency is equal to carbon, not 6, carbon minus 1/2 of the hydrogens plus minus 1/2 of the halogens, which we don't have any, so that'll be good, plus 1/2 of the nitrogens plus 1. Okay, so let's plug our empirical formula we have into this formula and figure out what we have. So we have C is 6 minus 1/2 of the hydrogens. We ended up with 12 hydrogens, so 1/2 of the hydrogens is 6. Okay. Minus the halogens is 0, because we have 0 halogens, plus 1/2 of the nitrogens, which is 1, because we have 2 nitrogens, plus, change colors here, plus 1. So this is going to equal to, so 6 and 6 cancel out, so we have 1 plus 1. So we have a hydrogen deficiency of 2. Okay. So to answer the question that I asked, how many rings plus pi bonds must be present in the structure? 2 rings, or 2 pi bonds, or 1 ring and 1 pi bond. Because we have a total deficiency of 2, which means it can be, each deficiency is a ring or a pi bond. So it can be 2 rings, 2 pi bonds, or 1 of each. And that satisfies our rule. Okay. Do we see how to use that hydrogen deficiency to help us down select again? We down selected from only carbon and hydrogen down to the right number of hydrogens, down to how many rings and how many double bonds we might have. Okay. So that's how to use those first rules. Okay. Now, in the second thing we're going to look at using some fragmentation patterns. Okay. So let's look at this as a fragmentation pattern and say, okay, let's figure out what we have here. So let's go to our table right here. And do we have a fragment that's 156? So 156 actually runs right off the top of this table. There's not a 156 on our table here. So, okay. What's the next most prevalent ion we have?
127.
127. Okay, and 127 we know is
Iodine.
iodine because it is the primary thing at 127. So we have iodine. So if we have this identified as, I'm gonna identify it as a halogen here, iodine, right here, that tells us that 127 minus 57 is the rest of the molecule, right? So if this was our parent ion peak right here, that means that our molecular weight of the rest of the compound has to be this minus 127. And I don't want to do math on the...
25.
It's 25?
Yes.
25? 25, really? The 7 to
Sorry, it's not 25.
29. I get 20.
29. Yes, 29.
All right. So if we look at our table here and look at what we see at 29, we see a C2H5. So 29 is exactly C2H5, C2H5. And notice we see a nice 29 peak down here. So even if we didn't want to do fast math like that, we could say, well, let's look at this peak here. So if we add that peak to that peak, we get that peak. So that's another way to do this quickly as we go through it. But it's important that you kind of know it both ways. So you pick one way and you just do it that way all the time. So we have 29, which is equal to this. So we have this fragment is this without iodine, which means our iodine has to be there. Right? Those are our only two fragments. We have our parent ion fragment, we lose iodine, we get this fragment, and then we have nothing else of interest in our system. So that means our compound has to be made up of those two primary fragments, and there's only one way to link them together. Does that make sense?
Yes.
All right. Okay, so like I said, we're trying to use all those rules we had. All right, so let's look at the next one here. Ooh, all right. Right away, what are you going to tell me?
Bromine?
Yes, bromine.
Okay, so we're looking at bromine. And because this splitting here and this splitting here are about the same and they both look like they have bromine, I think that this still has bromine on it. That fragment still has bromine on it. This is our parent ion peak with the bromine on it. This is that, and then this is bromine. See, it's 79 and 81. That's the bromine peak there. So what we see here is that these two fragments here at least have bromine on them. Okay, so what's the difference between this peak and this peak to tell us what broke off? Okay, and again, I'm going to go to my lovely computer here. 94 minus 38 is equal to 44. So if we're looking at the front peak on both of these, that difference is 44. Well, let's do the other one too. We have 96 minus 140. So that also, so if we're using this peak and that peak here, we also get 44. Okay, so it's important that you use the same peak to measure the difference. So if you use the front peak or the leftmost peak, then use both leftmost peaks. If you're using the right peak, use the both rightmost peaks. Okay, so that's telling us we have 44, and luckily there's a fragment here that's 45. It's pretty close. So if we look at our table, our 44 fragment is CO2, C2O, Oh, so there's a good fragment there that is CH2COH. So there's an aldehyde there. CO2, nitrogen, probably not nitrogen in the system because our parent ion pink is not odd. So it's probably not one of the nitrogens. So we're looking at a fragment that looks something like HCH2. This is our 44 fragment right here, okay? So we have bromine, and then a 44 fragment comes off, and so that means that we had that right there. So that'll get us down to this peak here. So this fragment broke off something with bromine. And then let's see what else. If that broke off, what's the difference between these two here? We need to look at that next. So 94 minus 44 is equal to 50. Okay. So what else do we have here that could be 50? Nothing is 50, but we do have a 49, which could be a CH2. Or, yeah, CH2 with a chlorine on it. So it might not be that, but we also, what else do we peak? We have a 45. The 45 is going to be that long chain alcohol too. 45 could also be COH, hydrogen, 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 hydrogen. Okay. So this is actually the 45 fragment. This would be the 44 fragment. Okay. And this difference is exactly 50. So based on what we have here, the bromine was on it with a 44 fragment, which would be 2 carbons, and the loss of a hydrogen here would give us that, and then that would give us that. What do we have? What do we have? So I think we have so what would the molecular weight of that compound be? We would have 79 plus 2 carbons, which would be 24 plus 1, 2, 3, 4, 5 hydrogens plus oxygen. What's that molecular weight now? Are we high enough in molecular weight yet? 79 plus 24 plus 5 plus 16 gives us a 124. We're still missing a couple, 1, 2, 4, minus 138. We're still missing 14. That means we need to have at least one more CH2 in our system. So it can't be that, it has to be OH. One more carbon, Br. Okay. So it has to be this propyl alcohol with a bromine on it. Because what we have is that. Now, let's figure out why. Okay, so when we have our first loss here, we have our loss, but it still has a bromine on it, right? Remember, when we have one of our fragmentation patterns is if we have an alcohol on here, or a heteroatom here, we want it to cleave opposite that so that we can form that 3-atom system coming off. So we're looking at that heteroatom fragmentation, telling us that that splits off, giving us a bromine with a CH2 on it. And then this last CH2 breaks off to give us our free bromine. So I bet if we added bromine plus CH2, we'd end up with this as our fragment. So what's our 94? If we look at our table, 94 is not listed, but oh, a CH2 with a bromine is 93. So we have to take each piece of information given and then make sure that all the pieces fit together. Okay, so the pieces we started with were, we had bromine on it, and we had something break off. I had a fragment of 44 break off, and the bromine was still on something. And then something broke off of the bromine. Yes, question. You're muted.
How do you know if you can look at, so I'm also looking at the appendix B. So how do you know if you can, so I mean, how do I say this? So we were looking at, for example, differences of 44 and 45 between the second bromine peak, the second peak containing bromine and the one without it. And then we were freely looking at fragments with weights 44 and 45. So I guess my question is, how do you know if you can be like, oh, this piece of information from the 45 fragment does not match. Let me look at 44.
Great question. And remember, when the difference between 45 and 44 is the loss of a hydrogen. Okay, so we're looking at something that is, number one, very easy to lose, and all you have to do is fragment it in a slightly different way. So what you would typically look for is your mass plus or minus 1. And you're looking for to build that, that piece of information. But notice how we kept adding information to the system. And then we took information away when it didn't fit the other fragments, okay? So now all the fragments fit together, right? So that's why, you know, it's kind of a puzzle problem in the fact that you have to take the ones that you have and, oh yeah, these were emailed out ahead of time. And I'm gonna email them out and upload them on tracks earlier next time. I just found these too late to do this. Sorry, answering a question in the chat room now. Okay, so what I want to do is I want to go through the argument one more time now that we've done it slowly, but have you do it kind of almost a speed run for it right here. And so the key things that tell us we had that is we knew certain things came off, but our mass didn't end up being exactly as high as we should be. So if we speed run our analysis of this thing right here, the first thing we see is bromine. So boom, bromine, we know there. And the second thing we see is that this fragmentation gives us bromine with a CH2 on it, okay? Because the 94, 93 is a bromine with a CH2 on it, okay? So that fragment tells us that. And the fragment that's lost here, the 44, tells us that is C2H3, no, H5O. That fragment was the one coming off as well. Okay, so we've built this fragment from here, this fragment from here, and this from there. And so now we also see that there's a loss to give us free bromine. This is free bromine by itself. The difference here is 14. So that's the loss of this fragment here. So we've already lost this fragment before we lose that fragment, so it must appear in the final. Now, what would be really helpful is to look at an IR, because if we looked at an IR, we would see that we have an alcohol, or we would see we have a ketone. And so we can eliminate a couple different choices at that point. So once we get to adding IR to this, we're going to get more and more complex. But you see where each piece of information came from. And then we had to add them all together to say, okay, well, a bromine plus 3 carbons plus an oxygen plus all the hydrogens equals our parent ion. Okay? This is kind of the thought process I want you to start thinking about as we do these problems. Okay?
I had 2 questions.
Okay.
Just to clarify, the loss of 44 between the first 2 major peaks also shows, you also see a peak at 45. Are those correlated? Like that loss of 44 also shows up as its own peak?
It should.
Okay.
Now,
And then,
way to do that is to have it, you know, and notice it's an M+1, it's a 45 instead of the 44. That's pretty common to, when it's ionized, to gain a hydrogen or lose a hydrogen. So
Okay.
+(-1) is acceptable in fragmentation.
Okay, so that kind of leads into my other question. The difference between 44 and 45 does not have to do with the unit resolution of plus or minus like 1 AMU?
It can, but again, the loss of a single hydrogen in fragmentation is really common. So I think that might be, you know, the idea of the 1 AMU is resolution, meaning that you only get to whole numbers. You're not getting to, you know, that's what we mean by 1 unit resolution, is that you're getting to a whole number. The plus or minus 1 has everything to do with the idea of losing a hydrogen here or there. Because once you have this ionized field, it's going to be pretty easy to ionize that and create a radical hydrogen and have it leave. And when we're going to have another exercise, we actually calculate out exact mass versus unit mass. And that's going to be next week. So when we do exact mass, that's the 4 places after the decimal. And we get really, really good about exactly how many of each element we have in this. Okay, we are still in 12:30. Ooh, we got 15 minutes. All right. Well, okay, maybe not 15. All right. Questions about this? Okay, the how to attack these problems is what I really want you to learn. Okay, and how to use this table. And you know, you can get a piece of a fragment and say, oh, it's got to be this fragment, but it has to fit all the other data. You gotta be willing to say, okay, I was wrong about that fragment. It's got to be something else. Yeah. So you want to fit it all together, and when it all fits together, you're most likely right. Okay. All right. So let's try another one. We're not going to do that one. All right. Let's look at this. Okay. And just by looking at, not to go away. Looking at this fragmentation pattern, it could be one of these different things, okay? And it could be that based on, you know, what we see and what we see. So let's start breaking up. Let's look at our major fragments first to see what we see. And then if we look at our other components and see what fragments we should be seeing them come off by looking at the fragmentation rules that we had on what we want to see. Okay, so I'm going to do in blue here, what are our major differences here? So this is 15, the difference between these two. The difference between this two is, let's see, that's 16, right? 59, so 15 and 16, so that could be a CH3, a CH2, a CH3, a CH4. And then 41, what is 41 in our book here? That's a very big fragment. It's a C3H5, which would tell us maybe a straight chain hydrocarbon. It's also a nitrogen containing fragment, but we don't have nitrogen in their compound, so we don't have to worry about that. So let's look for something that also has, ooh, there's a 42 here. That could have a fragment with oxygen in it as well. So that could be, a 42 could be a CH3 with a carbonyl on it. Okay, and that's important because we have some compounds over here with carbonyls. Okay, so we have those as our major differences here. So 15 and 16, 15 would be a CH3, and this would be a CH3 plus a hydrogen, right? Because that'd be 16. So just from that fragmentation, it looks like we're losing maybe a CH3 by itself, a CH3 by itself, or 2 CH3s, maybe a C2H, C2 if we're going from here to here. And we're getting a fragment over here of CH3H5. So that being said, let's start thinking about how we could break these things apart. Okay, So let's start with this one, because this follows one of our rules, okay? What mass do we expect to be our primary mass from something like this? Okay, if it's a ring, remember the rings are much more stable. And so it would clip off an oxygen and remain the ring, okay? So what would a ring be by itself? I believe it's gonna be a C6H10 is one of our fragments at C6H10 should be 90 something. We really don't see a 90 something. The loss of 16, actually be 85. That might be a plausible one there. And then, so that would be clipping off this. But then it wants to clip off another methyl group somewhere. Maybe not. Okay. So let's look at how we expect this one to fragment. Okay. So when we think about this one, we expect this one to fragment by doing this right here as our major fragmentation, because we're looking for our carbocation right here as a very stable carbocation. So we should have a C4 H9 as a major fragment, which would be C4H9 is one of our major fragments at 57. We don't see a major peak at 57. Okay. See why I want that peak at 57 to be there? Because this is going to be a major fragmentation. It follows the cleavage near a heteroatom rule, because we have a heteroatom here, which says that we want to cleave it here and give us this charge fragment, and it wants to cleave here because it gives this fragment with the tertiary carbocation. Okay, so this is not very plausible because of the loss of the CH2. If we lost a CH2 and an oxygen, that would make sense. So that would be something else, like a CH2 and an oxygen. That would make sense. But so this isn't very plausible either because the fragmentation's wrong. Okay, so let's look at this one right here. So we have the loss of 15 and 16, so that could be this one and this one, giving us what fragment would be in this middle section. That would be a C4. Is that one of our major fragments here? C4O. That's a fragment. It should be in the, is it 69? The 69 fragment that would be that? 1, 2, 3, 4, 5. Hey, the fragment 69 would be 4 carbons and an oxygen, the loss of some hydrogens. So that's a maybe still, because we can lose this section, and have that as a major peak. Then once this breaks apart, it would have to give us a fragment maybe like that. So that's maybe. But remember, those rings are stable. So this should be, you know, this part right here should be our biggest peak. And that might be it there. Okay, let's, so this is a maybe. Let's look at this one right here. Right here, so we have this fragment here as a major fragment, so that would be breaking it here. We could also have it as a C3, so we could do, let's see, cleavage here would be a 15, cleavage here would be a 16, cleavage here because of the heteroatom, that would give us a fragment there as well. So that's a maybe, but the most stable fragment for this would be this bigger fragment, which would be the C3H5. And we see that in our 41. So that's a maybe. In fact, this fragment and this fragment are both broken out of that. Let's see, this is a major fragment, would probably be this, a C2H50. C2H50 should be somewhere in the 40s range, probably a 45. That would give us a major fragment at 45. We don't really see a major fragment here at 45. So I don't think that's our thing. This would give us a major fragment at 1 methyl group and 1 oxygen, which is 15 plus oxygen. Ooh, 15 plus oxygen. Ooh, ooh. Giving us our major fragment. This fragment here is 69. So we have a methyl group plus an oxygen giving us a major fragment, which then can decompose, giving us our 2 other fragments here. So the fact that this loss of 16 and the loss of 15, I think most supports the idea that we have this methoxy here. And yes, I chose it last for a reason. But we lose this right here, that's exactly 15. We use exactly this, that's exactly 16. We lose this right here, it's exactly this fragment. And then we're left with a CO, which would be hidden under here as well. No, it's not. Yeah, no, CO is right over here. So, given the evidence, we could definitely eliminate these 2 right away because they didn't have rings, because they didn't have that T-butyl group. We could eliminate this one because this fragment wasn't seen right here. This is possible with a 15 and a 15, but we had a 15 and a 16. So that wasn't a good fit, but a maybe. This one right here, we just don't have the right fragments. We have one of the right fragments, but then this would give us a larger one, which would give us something here. So the best fit is this one right here. Okay. So see how you use the logical deduction. You start with what you have, and then you start eliminating based on what fragments you expect to see. Okay? All right, well, that's butting us right up against 12:25. And so I would like to answer questions at this time. And there are a couple other problems on this thing I emailed out. So if you wanted to go ahead and try to tell the difference between these 2 right here, and the hint on this number 6 here is that notice one of them you have bromine in your fragment and one of them you don't have bromine in your fragment. So that might play an important role in identifying which. And then go ahead and see if you can separate these. And again, this right here, the trick for this answer is going to be you're looking for that tropylium. The tropylium means you had a CH2 next to your benzene ring, okay? So if you have a strong 91, which this is, then you're looking for that thing that has to have a CH2 next to the benzene ring. So I think just by looking at those 3 things, you can say which one does not appear there. Okay, so go ahead and just kind of work through those a little bit. We're going to do another problem set and a little more lecturing on how to use this. You use the table in the book. And we're going to do another problem set and start to refine our problem solving skills with mass spec. Okay? Any more questions before we head out?
Did you say that we had a homework assignment?
We will have a homework assignment in the chapter 1, but it's not going to be due till next week. Okay? So I will assign it after we talk through a couple more problem solvings. Okay? All right, and I will email the the problems we're going to solve out earlier so that we have more time to prepare, okay? All right, well, thank you very much, and I hope to see you next Tuesday. I'm going to go ahead and stop recording.